Okay, hello and good evening. I hope you all are having a really good week. A very warm welcome to all the people attending this webinar today on an exciting topic, Accelerate Data Science Workloads with GPUs. To set the context, although the data science is transformational and key to unlocking value for business, data scientists typically face a critical challenge of having a slow processing power of CPUs. As a matter of fact, with the ends of Moore's law, the CPUs aren't getting significantly faster year after year. However, NVIDIA's GPUs can help data scientists achieve two key benefits: faster time to insights and more iterations on the datasets, which leads to better model accuracy. To know more about these GPUs and SDKs and how it can accelerate the data science projects, we have organized this session. To lead this webinar, we have with us Mr. Saurav Agarwal, the Senior Enterprise Architect, Big Data, Advanced Analytics and ML at NVIDIA, who has around 10 years of data industry experience implementing AI and data science, as well as analytical solutions on big data platforms. Saurav has also been a key part in multiple large-scale projects covering end-to-end data landscape solutions for automotive industry, supply chain, healthcare, banks, and even more. The session will have a 10 minutes Q&A after Saurav's presentation, so please drop in your queries on the chat or on the questions tab. Without any further delay, I would like to welcome Saurav for this webinar session. Welcome, Saurav.
Thank you, Sejuti. Hey, everyone. Good evening, good morning, wherever you are. Thanks for introducing me, Sejuti, but just reiterating or reintroducing me in a brief, I'm working as a Senior Solutions Architect at NVIDIA. And I am excited to present to you today about accelerating data science workloads using GPUs. So how you can use GPUs to accelerate your traditional data science or machine learning pipeline from end to end. So without much ado, so I'll start with the agenda, what I'm going to discuss in this particular session today. So we'll start with introduction to accelerated data science and what is RAPIDS ecosystem. So we'll start with what is difference between data science and accelerated data science, why we are calling it accelerated data science, and how RAPIDS ecosystem fits into the equation. Then I'll talk about accelerated data preparation and machine learning. That means I'll break down the data pipeline into multiple parts, and I'll start with, say, data preparation, and then I will go to machine learning, and then I'll explain that how you can accelerate each and every step of your data science pipeline. Then I will start with how you can scale your ETL and machine learning workloads in terms of when you have big data kind of environments, or maybe your data sizes are humongous in terabytes or petabyte scale. So how a single system or a single machine is not able to efficiently process and train the data. So how you can use multiple systems or multiple in a distributed or a parallel manner to scale the entire process end to end. Then after that, I'll be discussing about how you can do inferencing and hyperparameter optimization. So we all know that it's not only about machine learning training. When we want to deploy our data science and machine learning models, we also have to think about, number one, how to tune the models. So we generally use various hyperparameter optimization techniques. And number two, after deploying the model, we also have to understand that how we can efficiently make it available for inferencing. So in terms of how we can make it ready to use by thousands and millions of requests at a time, right? So you have the model ready, but how you can request and get your prediction done instantly. And finally, I'll talk about model explainability and also some parts of the visualization pipeline. So every data, exploratory data analysis or business intelligence kind of pipeline needs visualization as well. So how you can accelerate those or make a performant visualization dashboard as well. And also how you can efficiently explain the model using various techniques which are getting very popular nowadays, and how finally GPUs can help you do the end-to-end performance optimization, acceleration, and scalable processing. Okay, so I hope you are all on board with this, and let me start with a very fundamental aspect of accelerated data science, that is the GPU, the hardware. So every time we think about optimization or performance, we always think about software or configurations or some kind of in-memory processing. But what about the processing, right? So we have traditionally been using CPUs, which are good, and the cores of the CPU are increasing day by day. However, when it comes to a scalable and performant system where a lot of parallelization requirement is there and iterative processing is there, so there still there is a lot of scope of improvement on the CPUs. So what is the advantage that GPUs are giving? So GPUs were initially meant for graphical purposes. That's why the GPU full form is graphical processing unit. However, right now it is being used as a number one alternative of CPUs for accelerated data science, artificial intelligence, data processing, and so on and so forth. So how and where? What is the underlying fundamental hardware which is helping it to do it? So if you see this particular diagram, so there are multiple GPUs which are interconnected to each other, and these are in turn connected with the CPUs and the memory of the system. So this connection can be using PCI switch, or it can be some other networking fabric. So I'll let me explain that to you in detail. So first of all, the biggest advantage GPUs give to a particular user is the cores. So we always have limited number of cores, though the cores are increasing in CPU as well, day by day, 64 cores, 128 cores, so, and more cores are being added. But when it comes to GPUs, there are thousands of cores in a single GPU. So take an example of a RTX 3080. So there are more than 6,000 cores in that particular one GPU. So that is the reason why that thousands of cores gives up to 20 teraflops of general purpose compute performance. So the compute performance is measured in unit called flops. In terms of GPU compute performance, it can go up to 20 or more than 20 teraflops. And then from the memory bandwidth, so how much memory bandwidth can accompany? So for example, if you are using a Intel or AMD CPU, so you cannot scale your memory to make it so large that CPU can also be made so large. So there is no if you add suppose 10 terabytes of for example RAM, that doesn't mean that you'll be able to add that much number of cores in the CPU, right? So that is the bottleneck. It has that the memory bandwidth is good, is improving day by day, but still there are limitations to it. So here in terms of GPU, so you can get up to 1.5 terabytes of memory bandwidth, which is really humongous and can help you process data not only using the high throughput ratio, but also using the in-memory and using the memory a lot from the bandwidth perspective. The third part is the interconnect. So suppose we know that when it comes to distributed processing or multiple processing or parallel processing, so there we have to scale the hardware. So instead of using one CPU or one GPU, you have to use multiple CPUs or multiple GPUs. So in those scenarios, you cannot use very limited bandwidth interconnects like the normal maybe Ethernet 1G, 10G. So that will limit the amount of data being transferred from one GPU to other GPU, right? So that is the reason why what NVIDIA GPUs are capable of using accelerated interconnects as well. So these interconnects are in the form of NV switch, PCI switches, and Linux NICs and Infinity Fabric. So this Infinity Fabric is nothing but InfiniBand or something like RDMA over Converged Ethernet. We also call it Rocky. So that accelerates the data transfer between the nodes or between the GPUs as well. So in addition to being highly performant in the throughput, So if you need some kind of parallel or distributed processing, so in those scenarios also the networking acceleration, which is going up to 600 GB per second, is further improving the performance a lot. And it can scale up to 16x GPUs in a single node. So we have DGX 800 systems where you can have like many GPUs, around 8 GPUs in a single node, and can scale up to 16 GPUs as well in some scenarios. So that is the reason why this machines, the DGX machines we have, are humongous, not only in size but also, I mean, not only in the performance but also in the optimized size as well. So that is the reason why GPUs have become ready to go hardware for accelerated computing. And in this particular session, from the accelerated computing, we will drill down to the accelerated data science part of it and understand how the data science workflows can be accelerated from both hardware and software perspective to achieve the business SLAs or real-time processing or the latency we want. So yeah, I think we are good. Please, guys, if you have any questions, feel free to put your questions in the chat box, and I'll be answering that after a few slides. Or there is also a Q&A questions box, so please you can prefer to use that, and please do make use of this time by asking any amount of questions you need. So now let's understand from the data science perspective, as I said, right? So we know that we have been traditionally doing CPU powered workflow, and we have been traditionally using CPUs. So when we talk about the pipeline, so how it is? So the pipeline is somewhat like it starts with, like, for example, you start with the normal pre-processing of the data, and then you, for example, after some time, you forgot to maybe add a feature. So you start with the configuring the ETL workflow, then you start the ETL workflow, and then maybe you can like wait for some time for the ETL workflow to be completed, and then after some time you again like you see that still the workflow is not completed, so I have to wait and get another coffee or something, and then you realize after the ETL workflow has run for 1 hour, 2 hours, you have forgotten to add a feature. So because of that, you have to again add that feature and then again restart the ETL workflow. So this becomes a lot cumbersome approach, but still we have to deal with it, and then we have to do various analysis of the data and find out, okay, this is not the way we have to write ETL. We have to change our approach based on the analysis we do, and we have to do some additional feature engineering. There are some unexpected null values which are stored as strings, so we have to handle that as well. So based on the data exploration, with time, you have to keep on doing some cleaning of the data, munging of the data, and acceleration of the data. After that, what you do is you restart the ETL workflow again, and then it almost is the late evening, and then again, I think the entire thing takes a lot of time, and the day of the data scientist is completely finished without even getting time to start the model training or so, right? So what the GPU is giving us, right? So the GPU powered workflow not only is helping you to reduce the latency and the business requirements of the SLAs and all, from the perspective of a data scientist or a data analyst or a data engineer, it is also helping them to further accelerate their entire day to be more productive and more useful to the business, right? So if you have been given a work and most of your time you are spending in waiting for the ETL workflow to be completed, then doesn't look good, right? So so here, if you see from the GPU powered workflow perspective, what you have to do is you have to just maybe start with the configuration, start ETL, and then okay, the ETL is finishing in lot lesser time as compared to this. If you see, if it was taking this much time here in the CPU power workload, it is getting completed in this much time. So again, definitely there will be same issues if forget to add the feature and unexpected null values and all that stuff is done. However, that will be completed in the first half of your day as a data scientist, right? So now the second half, maybe or maybe before that as well, you can utilize your time to do productive stuff like training the model, validating the model, testing the model, doing some hyperparameter optimization, some experimentations and repetition. So you are adding, at the end of the day, you are adding a lot of value to the business case rather than spending a lot of time just processing the data or preparing the data, right? So this is the advantage of using GPU powered workflows as compared to CPU powered workflow. So I hope everyone is on board with this. Please do let me know if you have any questions. Okay. Okay. If no questions, then I will start with. Okay, there is one question. How we can procure GPUs? So GPUs are available on both retail and non-retail outlets. So yeah, I think we also have tie-ups with OEMs like HP, Dell, etc., etc. So maybe you can get in contact with them. Now coming back to now coming back to this the second part of it. So how the GPU powered workflow can be realized in the GPU ecosystem, right? How you can realize? You cannot use the traditional tools because traditional tools are not meant for being run on GPUs, right? They are meant for run on CPUs because their design, whoever has developed, whether it is open source or not, they have not considered initially when they had developed. Maybe they are considering it now, but initially during the times they had developed, they had not considered GPU as a primary processing engine or compute engine for their particular software development kits, right? So what NVIDIA has come up with is a new platform for accelerated data science called Rapids. And this Rapids is a suite of open source software libraries, which gives you the freedom to execute end-to-end data science workflows and analytics pipelines entirely on the GPUs. So you don't have to worry about any performance issues. You don't have to worry about any challenges in meeting the business SLAs. However, you have to use GPUs and the Rapids ecosystem. But it is really easy to do that. So if you know that, definitely when we can divide the data science work pipeline, we can majorly divide the data science pipeline into three parts, maybe data preparation ETL part, model training part, and maybe visualization. It can be a part of exploratory analysis or it can be as a part of the business intelligence. So when it comes to Rapids, so how Rapids has provisioned various APIs or libraries for the users or developers to use it effectively. So starting with pre-processing CUIO CUDA-F. So let me tell you this, the naming convention of CUIO, CUDA-F, QM, and so on and so forth is coming from the CUDA word. And CUDA is the NVIDIA innovation which utilizes primitives for low-level compute and optimization, exposes GPU parallelism, and it enables high bandwidth memory speed through user-friendly interfaces. So we know that the user-friendly interfaces we have been using day in, day out are like Pandas, Scikit-learn, Apache Spark, or Dusk. So all these can be further enabled on GPUs right now. How they can be enabled? So these are the libraries. For pre-processing, we have CUIO, CUDA-F. For machine learning, we have QML. For graph analytics, we have QGraph. For visualization, we have QCrossFilter. And for deep learning, we have GPU-enabled TensorFlow, GPU-enabled PyTorch, and GPU-enabled MXNet. So all these libraries are using one open source project called Apache Arrow. Now, what is Apache Arrow? Apache Arrow is an open source project which enables to interact with the GPU memory more efficiently and with the GPUs more efficiently, effectively as compared to normal row by row processing. It enables columnar processing, and also it enables the seamless use of the data formats from one library to other, or one part of the pipeline to the other. So suppose you have developing the pre-processing in CUIO CUDA-X in GPUs, that doesn't mean that you have to write back to CPUs and then do the machine learning training. So directly you can interact with, say, from CUDA-X to cuML, and you can start your processing just like you do in pandas and scikit. You do the pre-processing in pandas, and then you can use the scikit for machine learning purpose, right? sklearn or scikit package. The same way you can do the same thing, and Apache Arrow has enabled us to do that. So this is the very high level view of Rapids, but we know that like most of you have come with a CPU background, and it will be easy if we relate the tooling of GPUs with the CPU, so that you can write, or maybe without additional effort or a lot of effort, migrate your CPU data pipeline to a GPU data pipeline, right? So here it is. If you see in explaining what traditionally has been used for CPU pipeline. So it starts with all pandas for pre-processing, and for machine learning scikit, for graph analytics NetworkX, for deep learning PyTorch, MXNet, TensorFlow, for Matplot, for visualization you can use Matplotlib or Plotly. And if you want to do that on a scalable system, right, where you want to have a big data kind of system where you have terabytes or petabytes of data, so definitely pandas will not work, right, to scale. So there you have to use something like Dusk or something like Spark, and use multiple nodes, maybe tens and hundreds of nodes, to scale your workloads or scale your data science pipeline to multiple nodes or multiple CPUs. So, however, it is very similar if you want to do it on GPU, just that some of the packages you have to import and configurations you have to do is different. Apart from that, everything is very similar. So, for example, if you are using pandas, you can use CUDA-X. If you are using sklearn, you can use cuML. If you are using NetworkX, you can use cuGraph. If you are using deep learning, you can use GPU-enabled deep learning libraries, visualization. We have cuCrossFilter. Okay, and also for multi-node processing or multi-GPU processing, you can use Spark on GPU and Dusk on GPU as well. So this is comparing apples to apples. So if you have these tooling in your existing data pipeline on the blue part, you can migrate to the green part. Let me see if we have any questions.
Saurabh, we have one question asking how to transform Python code to suit GPU architecture.
Yeah, so I'll come to that. As I said, if you have Python code, it depends on if you are using vanilla Python code, then we have something called PyCUDA. It is not mentioned in this because we are talking about data science pipelines. And if you have data science pipeline, then you must be definitely using Pandas, Spark, scikit-learn. And if you are using that, you just have to use our packages of CUDA-X, cuML, cuGraph instead of these packages. Now I will exactly tell you how you can migrate in the coming up slides.
Great.
Okay. Sample code also I'll be, so there is a question that is there any sample code available for demo, so I'll be sharing one sample code as well. Okay, so from the data pipeline, from the data science pipeline perspective, so if you see here, we have data collection and preparation. Then we have exploratory data analysis, data pipeline, I mean the ETL part of it. So this is the ETL part of it. Then we have the model training, evaluation and tuning. Then we have model inferencing and monitoring, and then deployment. So all this can be accelerated using Rapids. So data collection and preparation can be accelerated by CUDA-X or Spark on GPUs. For EDA also same CUDA-X and some what cuML can be used. Again here CUDA-X and Spark on GPUs can be used. Here we can purely use cuML, we can use XGBoost on GPU. We can use deep learning libraries on GPUs. And for inferencing, we can use something called Forest Inferencing Library. That is again a part of Rapids, which I'll come in detail to. And finally, deployment and monitoring can be done using, if you want to use visualization or if you want to create an UI, then you can use something like Plotly or Plotly Dash. So this is the end-to-end pipeline on how you can do it on Rapids. And again, if you want to scale, you can use Dusk, and also you can use Spark for each and every step. Now, why you will migrate, right? So the question comes, I've been telling about acceleration. So how much acceleration and like what is the advantage of migration, right? So what we did is we created one benchmark to compare the performance of CPU versus GPU. And we used around 200 GB CSV dataset and Rapids-based pipeline completed in those operations. So how we compared that with CPU and GPU, what is the performance? So when we ran that using Dusk for 20 nodes CPU, so it took around the three parts to it. The green part is the data load and preparation. The gray part is data conversion, and the green part is XGBoost model training. Okay, so the green part, if you see, and if we add all the three parts, then it becomes the entire data science pipeline. So if you see for 20 CPU nodes for this 200 GB CSV data set, it took around 8,763 seconds. And the billing for the cloud, so the billing for the cloud means that we used 8 virtual core CPUs with 52 GB RAM on the Google GCP platform. So the billing for this job was $23 approximately. So we thought that there is a room for improvement. So we scaled up to 13 nodes, 15 nodes, 100 nodes. But still, up to 100 nodes also, we were able to achieve maximum performance of 3,221 seconds. However, the billing went a lot more because we are adding more and more nodes, right? So definitely GPUs are a bit costly than CPUs. If you compare one GPU with one CPU, definitely GPUs are a bit costly. However, the amount of work they can do is humongous. If you see this, we compared this 100 CPU nodes with 16 A100 GPUs in the Rapids version 0.15. And we saw that still, just if we use 16 A100s, we are able to complete that workflow in just 126 seconds, right? So in as compared to 3,221 seconds, right? So because of that, we saw 70x of performance gain, even if we use 16 A100s. And when it comes to billing, definitely GPUs are a bit costly, but when it comes to billing, it just for the same amount of work, same data science pipeline, which was running on 100 CPU nodes, which completed in 126 seconds, the billing was just $22. So we just saved 20x cost as well. Not only we gained 70x faster performance, but also we gained 20x better cost. So we had to pay 20x lower the cost to the Google Cloud as compared to the CPU configuration. So that is the advantage of migrating, and that is the primary reason you will migrate. Though this benchmark is just indicative benchmark, it doesn't mean that each and every workflow you will get at least 70x or at least 20x. It depends on various factors what you have been using, but yes, it is applicable for most of the things. So let me show you like some more benchmarks around it. So XGBoost, if you see, we did another training benchmark and compared 100 CPU nodes with 16800s. The time we reduced was from 1948 seconds to 87 seconds again. So QML is again powering your workflows with accelerated training as well as accelerated inferencing. So let's understand what all algorithms are possible in QML for accelerated training, right? So if you see here, we have almost all the algorithms which are available in the sklearn package being available in the QML package as well. So be it a decision tree, be it a linear regression, be it a logistic regression, be it a KNN, so on and so forth, like all kinds of pre-processing, all kinds of clustering, dimension reduction, decomposition, time series, cross-validation, hyperparameter optimization. All these are available, and every 15 days, if something is not available. So I'm not saying that almost 100 and 100.00% whatever is available in CPU is available on GPU. However, we are striving hard, and every 15 days we are releasing new version of this Rapids library to accelerate your pipeline and make all the APIs which are available in Pandas and sklearn being available in QDF and QML. So here are some benchmarks for various other algorithms. So as I said, that not each and every algorithm will give us 70x performance. So here we are comparing one V100 GPU with two 20-core CPUs. So this is the comparison we are doing. So if we see that for different 1 million rows, 2 million rows, 4 million rows, we are getting the GPU speed up over CPU. So here the random forest is giving the most GPU speed up as compared to PCA, linear regression, and so on and so forth. So some algorithms are very much accelerated, some are lesser accelerated, but still they are accelerated. So at least like you can expect 20x performance gain, and it can go up to 1000x or more. Okay, so that is the advantage. And then from the perspective of scalability, so if you see, if we add more and more data, then we are getting more and more acceleration as well. So why? Because GPUs are not meant for processing, say, some KB or few 1 or 2 MBs of data. They are meant because it can give high throughputs for humongous amount of data, right? So if your data size increases, then the speed up will further increase with the increase of data size, right? So if you see, most of the times, not all, but yes, most of the times those are linearly increasing based on the data size increment. So there's one question: can Dusk overtake Spark because of GPU? So right now the GPU can be accelerated on both Dusk and Spark. So there is no fight between Spark or Dusk. Both have its own pros and cons, and both have its own applicability. So I'll come to that when I'll come to Dusk. Okay. Now how you will migrate, right? So there was a question that how you can migrate your code from CPU code to GPU code, right? So let's understand how you can migrate that. So if you see this on the left hand side, it was a traditional CPU workflow, which is made of XGBoost, and we are importing XGBoost library. We are passing all the parameters, then we are doing the data conversion training. So this is how normal, simple, if you simplify the XGBoost, it works like this from the code perspective, right? So if you want to migrate to GPU, in addition to, definitely you should have the GPU access and the CUDA toolkit installed in your systems. But from as a developer, as a data scientist, you just have to add this parameter tree_method GPU_hist, right? So as soon as you add this particular parameter, this entire workflow starts running on GPUs as compared to CPUs. So that is the biggest advantage the GPUs are giving, that you don't have to rewrite your entire code or rewrite your entire pipeline so that you can accelerate up to 20x, 30x, 40x and more. You just have to add some parameter changes, do some import changes, and it can be done. Right. So yeah, so this is how easy it is to do it. So as an architect or as a data scientist or as a developer, this will be my huge concern that, hey, definitely I want to get 20x, 30x, 40x performance, but what about the effort for migration? So no, it is not a lot. Definitely, as you can see this particular slide, how easy it is to migrate to GPU from the XGBoost perspective. So though it is not this exactly the same for all the algorithms, that doesn't mean that for each and every algorithm, be it linear regression or logistic regression, you just add tree method GPUs. It's not like that. You have different techniques. I'll come to that, how to migrate, but it is really easy at a level of developer to do it by their own. Can freshers start learning Dusk instead of Spark with GPUs? Definitely, you can learn both Dusk and Spark. Dusk is meant for certain use cases. Spark is meant for certain use cases. Again, I'll come to that. Now talking about inferencing, right? So like the proof of the pudding lies in eating it, right? So because if you have developed faster algorithm to train, but you are not able to cater to the inferencing part of it, your inferencing is very slow, that doesn't look good on the entire pipeline, right? The training is happening in minutes, but the inference is taking a lot of time. So how you can accelerate the inferencing part as well? Like when you deploy the model, you have to do a dot predict, and then maybe spam or not spam, positive sentiment, negative sentiment. You have to predict it in real time, right? So you have to fetch that data as soon as you enter the data, you have to get that prediction out and send it to the consumers, right? So how you can do it? Number one, at scale, and number two, in the performant manner. So first of all, there is a library called Forest Inferencing Library inside Rapids, which helps to do that. Mainly, as of now, random forest and boosted decision trees are supported in it, like XGBoost, LightGBM, RF, and random forest has also come. And if you see the performance gain here as well, if we compare on various data sets available on the internet, the Bosch data set, or the airline, or the Higgs, or the Epsilon data set. So we did some benchmarking on these data sets as well, and we found that around, if we compare CPU time of say XGBoost inferencing with 40 cores of CPU versus GPU inferencing with 1 V100 only, so we are still seeing up to from 23x up to 36x performance gain. So we changed the data set, still the performance numbers were not decreasing a lot, they were consistent. So here, if you can see that not only the training, but also the inferencing part is also accelerated. Now talking about Dusk, because a lot of you are interested in understanding Dusk. So let's understand Dusk. Okay. So what is Dusk all about? So Dusk is all about distributed data frame. So we know that till this time we were using Dusk on CPUs, but let me tell you that Dusk can also be used on GPU for multi-node and multi-GPU processing as well. So how you can do that? How Dusk does it is it basically, if you have a smaller data frame, like maybe of date range February 2016, but that is not enough to fit in your single node machine. So what you can do is you can have multiple data frames, I mean multiple months of data, which can go up to terabytes and petabytes, right? So that terabytes and petabytes of size cannot be handled by single machine or single GPU, right? So you have to use multiple nodes or at least multiple GPUs to handle it. So what Dusk basically does, it chunks the data into multiple partitions, and those each and every partitions are limited in size, and those can be accommodated in a single GPUs, and those get processed in each of the, like at the partition level, and then the results are merged together and shown to the user. So Dusk is a library for parallel scheduling. It can decompose large data frames into collection of data frames or series. It schedules and executes, optimizes task graph on one or more processes, threads, and so on and so forth, right? So Dusk task graph. So basically, see how it works is it creates a directed acyclic graph. Now, when I talk about acyclic graph, that means it's like a tree structure, you can see, right? So how it works is, for example, you have Dusk data, and you are chunking it down to multiple partitions. And then the circles are the function calls, and the rectangles represent the data and the results. So initially you started with, these are the partition. You started with this many number of partitions, and then you ran some functions on top of the data. It can be increment function, double function, and so on and so forth, right? Then what you did is you found that you need to add those partitions up and calculate some kind of aggregation, like the basic aggregation of sum or an average, or maybe max or min, right? So in that scenario, you have to merge the data together, because all these data sets are lying on different partitions or different GPU nodes or CPU nodes, right? So there, by causing the need of merging the results, so whatever is possible on that particular node, that processing will be done. However, the entire processing cannot be done, and then the data needs to be merged together and executed, so thereby creating a thing like a directed acyclic graph. So this is how you can scale up your accelerated data science from single GPU to multiple GPUs as well. So if you have, suppose, a system like a DGX 800 where you have 8 GPUs, then you can utilize the entire 8 GPUs for processing your data. For a code snippet, how to do that exactly? So for example, if you see this particular code snippet, it's very much like pandas. So since somebody was asking that difference between Spark, so generally the suggestion is, if you are running, if you are a data scientist and using a lot of pandas, then there is a minimal pre-processing of the data needed, then and your use case is more of a data science heavy use case, then very well you can use Dusk for it, because the migration of the code is very similar to what is there in pandas and sklearn. So you can use Dusk. But suppose you are a data engineer or a big data engineer who is more focused on data ETL pipeline, creating some data lake or data warehouse, right? So in those scenarios, Spark is more suitable. So because there is a humongous amount of data and humongous amount of processing you need to do with the data. So in those scenarios, Spark is a better fit. Though both work on the similar concepts, multi-node, multi-GPU concept. However, the usage of Dusk and usage of Spark is for different use cases in the data pipeline of an organization. So let me take some questions. How a task is divided between multiple GPUs. So see, since the data is divided into partitions, right? So as I said, data is divided into partitions. So some of the partition go to, say, GPU 1, the other partition number 2. So this can be one partition, right? Just an example. The second partition can be this, and this can go to GPU 2, and so on and so forth, right? So at the base level, when you divide, you create a Dusk data frame, you create a distributed data frame. Then as and when you create the data frame, the data gets divided into multiple GPUs, right? Because you are telling the function that you have to chunk the data and send the different data sets to different GPUs, different partitions of the data set to different GPUs. So it is done as a part of the Dusk workflow. Now coming back to the pipeline, if you see this particular slide, so first how we can do the data pre-processing and feature engineering using GPUs. So first we need to convert the pandas data frame to Rapids, or you can load CSV data as well, or a Parquet data as well. Whatever data you have, you can load it. Then you can impute the missing values. So missing value imputation is there. Then you can normalize numerical values. Then you can do something like a one hot encoding. Then you can do target encoding. Then you can do normalization. So all this can be easily done in a distributed manner using Dusk. Now, how exactly the distribute function is working? So if you see, if device is equal to GPU, then and partitions becomes the number of workers. That means the number of GPU nodes it has. And then the Dusk ODF is created from the pandas data frame, and the Dusk data frame of x underscore Dusk, y underscore Dusk is created. Then if you are using CPU, then it's a CPU thing altogether. But this is how you can use the GPU part for data loading. So that was data loading and pre-processing of the data from the data science pipeline. Now, if you want to do it in do the machine learning in a distributed manner, so if it is a single node, and if you are using something like an sklearn, then what you can do is you can use sklearn ensemble, random forest classifier, and then max depth and beans entries and all that stuff you can use. And if you see here, this is a simple machine learning training pipeline using traditional sklearn library. However, if you want to migrate it to cuML, I mean using GPUs, so see how easy it is. Just that the changes are on the highlighted part. sklearn.ensemble will change to cuML.dask.ensemble. Okay, and in addition to that, if you want to do the Dask based, so you have to do all the things are similar, but you have to do the dot compute method. So what happens is it's like Spark. Like when you do all the transformation, it doesn't kick off the transformation. The transformation is kicked off by some action. So in Dask also, unless and until you write dot compute, the processing will not start. Right. So compute is telling the Dask process that you start the computation of all the data loading, processing, and so on and so forth stuff. Okay. So same way, so if you see how the data frames are divided, so if you see in case of XGBoost also, where the D matrix data format is supported, so GPU based Dask data frame is divided into multiple partitions, and partitions are divided across GPUs, as I said. So after data transformation is done, you can create a D matrix kind of format. Again, those D matrix will be sent to multiple. This can be sent to GPU 0. This can be sent to GPU 1, and so on and so forth. So here, if you see the example code for XGBoost, so same XGBoost as XGB, import Dask. You have to create XGBoost.dask.dask D matrix, and you have to create train and test data frames, and then parameters. You can add this particular parameter, which is of the paramount importance, the tree method GPU underscore hist. And apart from that, it is similar to the normal Dusk pipeline you have. So not a lot different than normal Dusk. And then you can do all the things like training, prediction, and all that stuff using the Rapids cuML on Dusk. So import XGB as Dusk, convert Dusk QDF to D matrix, set the XGBoost parameters, set the GPU for training algorithm using GPU underscore hist, pass client to XGBoost as Dusk, give the booster in trainer model, history is evaluation metric. So all the parameters you need to give in the .train method, and then GPU predictor instead of CPU predictor. So here, if you see the set param, again for inferencing, you have to add GPU prediction because you want to add prediction on multiple GPUs instead of multiple CPUs. So this is how you can do that, and then call .predict method to do the prediction. And as I said, until unless you use .compute, you will not be able to run the transformation. So .compute is important for kicking off the transformation. Any questions, guys, till now? Does Google Collab support QML? Yes, it supports. I will tell you exactly how to do that. Yes, Google Collab supports it. What is the use case at production grade? Everything is so many companies in the world are already using Rapids library in productions. So be it some retail giants, be it some pharma giants, a lot of companies are already using Rapids based libraries in production already. So all these what I'm explaining is already production grade and can be deployed in production environments. Though it is open source, so you can go to GitHub and see the repositories, see the things there as well, but all these are production grade. From the model explainability perspective, we know that SHAP package is the most used package for model explainability. So specifically the boosting models, if you want to see the feature importance based on the Shapley values, so you use the SHAP packages, right? So that SHAP packages basically are too computationally expensive if you use for large scale production based systems. So thereby, we thought that why can't we accelerate that as well? So we have come up with GPU tree SHAP as well, particularly for XGBoost, and we are getting 20x faster performance. And many companies have also started adopting it in India and overseas, and they are getting similar speedups for model explainability feature as well. So these are the sample result. You will be getting GPU accelerated SHAP values in a 20x performance gain manner. So yeah, as I told, forest inferencing library can be used in addition to SHAP for inferencing at scale. Okay, so I think yeah, this one is a repeat. Okay, now let's go to the hyperparameter optimization. So as we know that model tuning is a good important step. So definitely we have been using something like grid search CV or K cross validation and similar things. Apart from that, there are multiple open source libraries which do the hyperparameter optimization, and also there are multiple other open source libraries like Numba, Hugging Face, and so on and so forth. So all these are now like can be accelerated on GPUs. So for example, Blazing SQL at 10 TB shows 25% improvement over Dusk, and it's like kind of enables to run that on GPU. And some of the queries of GPU big data benchmark are more accurate with Hugging Face, so you can use that as well. So we have been comparing 10 TB scale to show rapid performance increasing over times when the total cost of ownership continues to go down, right? So definitely you can think from the integration to other sources, like if you are using Hugging Face, you are using Numba, you are using something else. So all that is integrated with Rapids. Apart from that, from the hyperparameter optimization, so we have integrations with libraries, popular libraries like Optuna. We have integration with libraries like Raytune. We have integrations with AutoGluon. So all these are hyperparameter optimization libraries, which will help you to further optimize your end-to-end machine learning model, so that you can get a better accuracy and better benchmark results as compared to without hyperparameter optimization. So same way, Optuna, Raytune, or if you run on GPU as compared to CPUs, again you can get more than 20x, 30x, 40x performance. So we have good integration with all the open source libraries in the world of data science, so that you can use those libraries on top of GPUs as well. Okay, so that is from the hyperparameter optimization. For visualization, we have cross filter, which is efficient GPU backed in browser visualization engine. Again, if you want to create some charts like a pie chart, bar chart, line chart, scatter plot, and similar things, you can create using cross filter. It is based on bokeh and data shader charts, and you can also do something like multiple charts. You can create a dashboard with multiple charts with cross filtering widgets. You can filter the data and see that, and it is built on PyVis ecosystem tools. So if you are using Python, it is best to migrate from say Seaborn or Matplotlib or the CPU based bokeh or data shader to GPU based cross filter. Now comes the important part. So as a data scientist, how would you start learning Rapids, and how you can master accelerated data science with Rapids? So first of all, I'll go step by step. So first of all, you have to go to a website called rapids.ai, and there you can see a lot of stuff already there, like how to get started, what is the community talking about, or what is community associate, what are the blogs, documentations, GitHub repositories. So how to get started is written. So somebody was asking how you can do Google Collab. So if you click on this, if you see in the get started page, try now online on Google Collab, just click on this. It will open a Collab notebook in your Google account, and you can start practicing UDF and QML, okay, on the Collab. But make sure that runtime you are using is GPU, and you are getting something like a Pascal or above, like a P100 or a T4 or a P4 and above GPU type. Otherwise, it will not work. So this is how you can do it in Collab, but other cloud service providers also do support Rapids, AWS, Amazon, Microsoft Azure, Google Cloud, everywhere it is supported. So different aspects of different cloud environments are given here. Then talking about the community, so all these community Rapids is associated with, and various blogs have been written, how you can accelerate DF, IDF, NLP processing, how you can streamline your model bits with PyCaret plus Rapids, how you can do Rapids and paper space gradient. So all the latest and greatest integrations and use cases and some sample code and sample notebooks you can get in the blog section, so that you can also practice yourself. The documentation, detailed API docs are available here. So if you want to see what all exactly libraries are present, so all the detailed library, like for example, for time series, we have what all things available. So at API level, at the library level, we can see that using this documentation. And then you can do hands-on Collab. As I said, you can download a container. So if you are familiar with Docker, so we also have a Rapids container available on our NGC. So you can do a Docker pull, and seamlessly you can use Rapids without the hassle of installing it using Conda or similar tools. There are documentation, and then we have this repository in in the open source GitHub, where you can see the source code of this being available, as well as if you want to do the practice of various types of use cases and notebooks, you can come to this notebooks-contrib folder link, and then various types of notebooks will be available, like Introduction to Rapids notebook and different notebooks, multi-GPU notebook, NLP notebooks, graph analytics, cybersecurity, so on and so forth. Different notebooks are available for you to practice Rapids. Okay, so I hope it is clear. The biggest advantage Rapids is giving is you can maximize your productivity as a data scientist and data engineer. You can get top model accuracy because you are increasing the amount of data, and you are able to tune the model very often as compared to CPU. The total cost of ownership is reduced, as I showed you in various benchmarks. We are targeting very easy to use language like Python and SQL. You don't have to learn any new programming language. You don't have to learn any new framework. Whatever is available in Pandas, scikit-learn, it is very similar to that. So don't have to learn anything. So I hope each and every one of you will definitely try that out, see the benefits of GPU computing without any much learning curve, and definitely use it in your day-to-day work as well. So this is the part you can download and deploy. I showed you, so you can get it from the NGC or you can get from open source Docker as well. So yeah, now I will open to more and more questions so that we cater to any doubts and problem statements people are facing.
Thank you, Saurav. Great session. Made a very complex subject very easy for a lot of the attendees to understand. We have a few questions. Let's dive into that. You have already taken a few during the session. So Danny wants to know, is there a library similar to OpenCV in Rapids for image processing for computer vision models?
So we don't have any image processing, but there is some library called QSIM. So if you go to this rapids.ai page, there is one library called QSIM, which is extended toolkit designed for GPU accelerated computer vision and image processing for n-dimensional images. So definitely, Dani, you can try the QSIM library. And definitely let me know if you have any further questions on this.
Correct. We have one more question from Yash, which asks, can you share some books or courses to learn Rapids?
See, I have shared this particular deck. I think has been already shared by Sejuti in the I think handouts section. So please download from that. And in this particular slide number 29, if you see, I have for you written step-by-step documentation to how to learn Rapids. Okay, so definitely we can also come up with some books in the near future. But as of now, this is hands-on approach is more effective approach to learn Rapids in a faster manner.
Correct. I hope that helps, Yash. One more question is on, are your HPO libraries available on Kaggle?
HPO libraries like Raytune, AutoGluon, I even have my own, definitely they are available. So you can go to my Kaggle as well, and there you can see that I have used HPO library like AutoGluon for using that. You can search my name and you can get it there. And yes, those are available to answer your question.
Okay, great. Rohan is asking, how is Pandas different from Python vanilla? I think it goes.
Okay, so yeah, Pandas is a data processing tool. It is generally used when we have tabular kind of data, structured data to be processed for data science or data engineering workloads, right? So it is quite different and it is quite performant, and it can be very easy to do processing using Pandas as compared to vanilla Python.
Correct. I hope that helps. Okay, Saurav is asking, is there any NVIDIA cloud for university education where students can be trained on such stack?
We do have DLIs, so you can just search for NVIDIA DLI, and we do conduct DLI very often. So what you can go is you can go to that NVIDIA DLI page, and you can see that there are a lot of DLI options available, including Rapids and data science, right? So these are the various online courses available. So definitely these are available for both individuals and universities and corporates. So definitely you can go and enroll yourself for that.
Correct. We have many questions coming in. However, we will take 2 for now, and then we'll wrap up, and then probably rest of the attendees can get in touch with Saurav, get them questions answered. Jyoti is asking, is there any tool in Rapids that can be used for NLP, especially for machine translation?
So for NLP, we have a different library called Nemo and Riva. So if you search NVIDIA Nemo and NVIDIA Riga, so these are the two most famous libraries we have for NLP and machine translation. So definitely these are not part of Rapids, but it works on the same aspect of GPU computing. So all the ASR, speech classification, recognition, and all that stuff, and also conversational AI, all this can be enabled by these two libraries.
Correct. Okay, let's take one more question for now, and let's then wrap up the session. Is it possible to include user libraries like using C, C++ into Rapid?
C++, definitely we have the Rapids built on top of C++. So it has something called, for example, if you want to use CUDA-X in C++, we have libCUDA-X. So if you can go, this is again open source. So this libCUDA-X is written in C++ and it is available for C++. So definitely, if you want, you can go. If you know C++, you can use C++ to do the same things.
Also, does Rapid support AWS and GCP?
Definitely, as I said, all three, yeah, it was already explained that all three environments, major cloud providers support Rapids.
Okay, so that brings us to the end of this session. Saurabh, thank you so much. Great, it was great insight from you. I hope your session helped the attendees, understand how data science pipeline works, how data science architecture, get them familiarized with the data science architecture, and of course how open source libraries can help speeding up their workflows. So the session was great, very interesting. Thank you so much, Saurabh. And I hope that the rest of the attendees can get in touch with Saurabh. Saurabh, if you want to share your contact details with them.
Yeah, sure. So you can do two things. One is you can go to LinkedIn, and there I have my profile. You can connect with me on LinkedIn. So the ID is /Saurabh Agarwal, AGARWAL. I'll probably put that in the chat box so it is easy to use that. And also I have my email ID here on the slide, saurabh@nvidia.com. So feel free to reach out to me in mail or LinkedIn so we can take it from there.
Correct. And all of the attendees who have asked for the PPT, everybody can access the PPT for in the handout section. So please go download it from the handout section, and there you will have Saurabh's ID as well for him to, for you to get in connect. So for now, thank you so much, Saurabh. Thank you so much for doing this webinar with us.
Thank you. Thanks a lot.
Thank you.